thank you so much for coming to mine and James' call. Talk about our experiments with API server. Unfortunately, James is not going to be here, but I'll try to do my best to run you through what we've been playing with lately in the API server, with the goal of providing users with a native multi-cluster experience. Again, this talk, for the people that have seen maybe last year talk about workspaces, from me and James, is very much like a kind of continuation of this kind of research in the API server that we've been doing. Unlike workspaces, which was focused on multi-tenancy, what we're going to be talking about today is more aggregation of resources across clusters. And you will also kind of see during the talk some of the motivation for us to build such features. And I'll try to leave 5 minutes at the very end for a question. I've been told that you need to go here in the line. But yeah, otherwise, we can just meet in the hallway track, I guess. So to begin with the talk, I really want to start talking about scalability. The reason why is that for a very long time, for customer or platform team implementing Kubernetes, the API server has been a very complicated application to scale. This is because when you start exposing the Kubernetes API to your users and you don't control the interaction with the API, the API server itself, for a long time, lacked some core features in order to kind of enable it to scale and reliably. And platform team found themselves wrestling around this software to protect essentially etcd from the load generated from the users. There are very good and well-documented best practices in the community around how to scale Kubernetes. For instance, for large cluster, the idea is to separate events which have a high churn rate from other resources into a separated etcd cluster. Prefer binary encoding via protobuf of the objects that are returned from the API server in order to reduce memory utilization. And also drive really work with your internal customer in order to make sure that every CRD has strong validation in order to prevent a situation where serialization becomes again a problem with memory. In the most recent Kubernetes releases, the community has been doing a fantastic job in kind of tackling some of these fundamental problems in the API server design, and in particular the fact that the API server itself doesn't have strong protection from certain client behavior. And I really like to call out the work that has been done around cyber serialization, in particular because CRD objects are encoded in JSON, and whenever the API server needs to return this kind of object to client, especially with big lists, it needs to deserialize and reserialize against this object, and it's very hard to manage a scale in terms of memory. Another very good feature that has been released is serving consistent reads from the cache. This is specifically because when you have clients that needs to list objects and then don't use properly the resource version semantic, this will result in all of the load going to etcd, and you cannot really scale horizontally etcd, so therefore all of the cluster performance is being impacted by these small clients. Last but not least, something that kind of also we've been hitting is that before the snapshotable API server cache, there were also some performance or issues when using server-side filtering of object. In particular, the API server was doing the filtering after returning all of the object from etcd, which again was causing a lot of issues with memory. So lot of good work lately from Kubernetes. However, when we look into scaling the API server, it's not only about nodes, it's not only about all of these things in the API server. There are a lot of implications also when building a platform. In particular, how you shard the controller, how you scale them out, because the more churn rate of object that you have, the more deep is the work queue of this controller. You might be looking into ways to kind of shard your platform and maybe not go for massively large cluster, but maybe chunk them in smaller pieces. The other thing which I think is something that for me is always interesting is running a platform team. They really want to provide customer with very well-defined full domains. We will see later about this. And every large cluster also means a huge surface of issues when become outages because of configuration changes and things like that. So what we try to do is also and a consideration that is important is how to limit the blast radius of changes. So in to the motivation like for us like to do these, about the motivation for us like to kind of do this work in the API server is really like kind of like what it means like building a platform on top of Kubernetes. I've been talking to someone like these days, and they kind of said like, oh, the holy grail of the platform engineer is provide powerful abstractions and that everyone buys in. And this is kind of really true, like it's so hard. I think Kubernetes has been doing a fantastic job in the community, and I mean, the room is full, on like providing very powerful abstraction around workload, but when we build the platform there is also a lot of like domain-specific knowledge that needs to go in, and as platform team, we're looking to abstract on behalf of our user. It's very important, therefore, like, to provide like this domain-specific workload abstraction, provide domain-specific like topology information to the user so that they can like spread their workload across like fault domains or maintenance domain, depending on how our platform are configured. As a platform team, also a very important element, and this is a bit of like the fight within the user and like the platform teams, is how we drive utilization while still enabling user like not to fight with it. Like again, like how many people here have been working around like tuning resource request and limits and this kind of aspect. And in general, like building a platform means being able like to manage the life cycle of the underlying cluster resources, either with your user having minimum impact, right? And that's like again. I think that Kubernetes does very well, but when you look into implementing in a specific context Kubernetes, there are way more features, way more things you want to provide there than what Kubernetes provides from default. With this in mind, like the kind of idea that we had is in the traditional sense, and this is what many of us and we also like have been using, is like this idea of cluster as a service, where a cluster is essentially like a cluster are mapped to teams, and each team has its own cluster that it kind of manage. However, at scale, something that we have also like considered is what are the alternatives to this approach? What if like customer want to scale beyond the single cluster boundaries, and how do we kind of like enable ourselves to slice and dice the infrastructure as we want without exposing this detail to the customer? And the idea that we had was really like, can we build like a very thin API server layer on front of the actual Kubernetes cluster that enable us as platform engineering team to have the ability to steer like the customer workload across cluster, add cluster, remove cluster, add nodes, scale them as we require, without exposing all of this information to them, or have to coordinate this effort with a lot of customer whenever like new capacity come online. The first building block that we're going to talk about in order to achieve this is like the multi-cluster scheduling. We will actually spend more time about like the API server because it's also very important. But for the multi-cluster scheduling, essentially what we found ourselves is that traditionally the Kubernetes scheduler works by having essentially like a deployment object and like kind of like generating via controller manager a bunch of pods and placing pods across like nodes. We wanted like to find like a very similar abstraction, but just for workload, and build something like that enables us like to kind of like get some deployment, workload, stateful set, jobs, and these kind of resources, and map them to cluster where the resources are available, and then like use the regular Kubernetes scheduler in order to kind of place the individual pods on the specific nodes. In our quest, like for looking for this solution, is where we find Multiqueue. Multiqueue is a community project generated by the working group batch, and it provides us with very, very powerful APIs in order to manage that. So the idea here is like, as a user, instead of submitting like a workload across an individual cluster, we'll now submit it against a multi-cluster API server, and then Multiqueue there will receive this kind of workload, reconcile this workload, map it to actually this deployment, map it to his internal like workload representation, pretty much similarly to what a pod is, find a cluster where like this deployment can be running, push it down, sync up the status, and then like in the actual cluster, what we will have like the standard like deployment controller generating like the pod object, and the standard scheduler binding the pods to the node in order to run them. With what we find in Multiqueue, and the reason why we decided to use Multiqueue for this is because actually like it's a very flexible and easy to extend framework. It comes with some opinions, like there are a lot of use cases for Multiqueue around like in the batch domain. We actually use it like for every workload. Like it's not only about batch for us, it's for any class of workload. It really is a way for us to have an API that allows us to abstract like this workload type and manage like the multi-cluster scheduling for them. One of the things that we've been really like kind of engaging and trying to collaborate with the community upstream is around like this kind of concept of elastic workloads. So how we can support the scale semantics, scale out that is, for instance, required for deployment. Because from the batch use case, like jobs are things that you dispatch and they're until completion, while for us, we want to support like more flexible use cases in order to hide entirely like everything like to our user and provide them a experience which is compatible and with what Kubernetes provided by default. Another thing that is very important, coming back like to the custom workload abstraction, is also having the possibility not only like to limit this work to core Kubernetes API type, but also do it like for our own specific like API types that we provide our customer as a way to build on top like stateful services beyond what Kubernetes provide by default, or like job workload and orchestrate them across our platform. And multi-queue support, and queue and multi-queue support that is essentially via the concept of external framework that allow you to have a controller that kind of like manage outside of queue the logic for their orchestration, while queue takes care of finding the capacity and placing them in the clusters. Having said that, like as I just said, like multi-queue has been like the solution for us like to kind of like implement this multi-cluster scheduling, but what about API server? And what we found about the API server is that we've been looking a lot at the community. There are a lot of like kind of like solutions, but for us, one of the things that was very important as a requirement is really like provide customer an experience as close as possible to what Kubernetes provide by default, just in a multi-cluster environment. To do so, we ended up like kind of implementing our own multi-cluster API server, build on top of what like the core Kubernetes API server code, essentially like extending the capabilities of the API server that are there by default and kind of like implement some more things in there in order like to deal with the multi-cluster scenario. In particular, one of the challenges when doing so is really about the list and watch semantic that the API server provide. Our goal was to enable controller talking to a multi-cluster API pretty much as they can talk to a regular Kubernetes API, and being able to establish a watch against like objects that now are spread across multiple clusters. So hiding, again, the placement entirely from them. And in order to do so, like the convention, the API server, what it's supposed to do is supposed to return, being able to return a list of objects with a specific resource version. And the resource version is really like the aspect that is very important here. We're going to talk more about. And because the resource version represents like a point-in-time reference, like in the underlying storage, in this case, like by default etcd, of when the data were produced, were returned. And data change all of the time, and it's important, the resource version, because then is what later the controller use in order to establish a watch and get a stream of events server-side generated about all of the updates that happen in the cluster. etcd is the default technology that enables like this in Kubernetes. In particular, the resource version is the version of etcd, essentially like that etcd keeps internally of the objects, and is coming really like from the Raft consensus that happens like in order to replicate like kind of information across nodes. However, the resource version is of a specific etcd like server. When we have multiple clusters, there are multiple etcds, so how do we provide like a similar semantic in a multi-cluster environment? The kind of naive approach we started with is really like, hey, can we model in the multi-cluster API server like this resource version as a vector of the resource version of each underlying cluster? There is actually like a very nice issue upstream, which I linked at the bottom of the slide, about why this is hard. In particular, the fact that a lot of clients, even if in theory like the API server should, the resource version is something we don't expect client to parse and make assumption on, the reality is that because it's been forever like a int64 number, many clients, and even in the Kubernetes core code, have been parsing this in order to implement like specific behavior. So the challenge was like that by implementing like this new resource version concept as a vector, the problem is that we would have been breaking some of the client assumption around like this specific field. And the other problem that we found is that, again, like coming to the flexibility we want to have as SRE is like adding, removing like cluster from like the multi-cluster API, then it becomes very complicated to model this semantic because it's hard like to have a total ordering of event when like you have members of this vector that goes, come and goes. We essentially move on from this approach, and then we started looking into another very naive approach. And what if we essentially kind of like were to have a controller, like that everything that it's doing is essentially watching for objects across the various clusters and creating this object in the multi-cluster API. Imagine like you have the multi-cluster scheduler that creates like a deployment, you have deployment spread across cluster, and then you have like this controller that watch across multiple clusters and create the pod, sync back the pod into the multi-cluster API server and etcd. That, again, like, while this approach actually works, like what we found is that this approach had like some fundamental limitation in terms of scalability, because then essentially what happens is that we have now a gigantic etcd that needs to store all of the objects of all of the clusters and becomes like a very complicated to scale, especially because one of like the things that we were looking for is also like how can we make this layer as much thin as possible in order like to provide like reliability, to be reliable, and provide us like the ability to scale beyond what a single cluster can do. Eventually, what we ended up with this idea of kind of reclocking events. And again, like if you kind of zoom out from this problem, the real thing that we want to do is, and the property we want to satisfy is have a monotonically increasing like version number, which is true across all of the clusters. So instead of like syncing back all of the objects to the multi-cluster layer, what we are essentially focused on doing was focusing on like just providing this feature through etcd. So like provide us like with a monotonically increased like resource version number across like different clusters without necessarily having to sync all of the objects, and you will see what this means. We do have still like some scalability concern about this, in particular about the rate of events. Is something that we are looking into like exploring how we can build on top of this sharding. And in particular, the idea that we have is potentially combining layers of this in order to enable us to scale more. But what we found out with this approach via our testing is essentially that because like these object representation is very tiny, we can actually have now options to either like offload it outside of etcd using a different storage, or keep using etcd and only like kind of, because it's very compact, like the only domain for scalability is essentially the rate of event and is not anymore the storage, which would be been the problem with the previous solution where we copy all of the objects. The fundamental structure that we have essentially to implement this logic is what we call this version marker object, as I said. And this version marker object is essentially consisting on 3 metadata. The store, which is the reference to the cluster where the object is coming from. The object, which is like a reference to the metadata, in particular the resource version of the object in the originating cluster. And then the template, which encodes in there like the metadata, in particular the new resource version, which is the unique across all of the cluster, like point in time in which this event has been observed. That is what we use essentially to implement like the list and watch semantic at the multi-cluster layer. You don't see like here in these specs like only the resource version field. We have like this template or object references, because some optimization we found like to scale out is by having also like support to label selector at the multi-cluster layer, and that's why there are a bit like more fields into that. But at the high level, you can imagine that these are essentially kind of like just resource version metadata. So how do things work into this multi-cluster work? You have a client that talks to a multi-cluster API, and all of like their get and list requests essentially eat like this watch cache, which is essentially implementing the storage interface of the API server. Normally it's implemented by etcd. Now we're implementing it essentially by this version marker store. And then what we have a request routing layer that essentially takes care of like deciding, like translating the representation in terms of resource version at the multi-cluster layer to the representation in the individual cluster of the object. And that's essentially what we are using in order to re-implement the storage interface with this and provide like our clients with the ability to offer consistent reads at the multi-cluster layer of the object without eating the underlying clusters. It's going to be more clear in the demo, hopefully. Last thing before we get into the demo is essentially like, how can we handle the other set of requests like that we need to do for these objects, in particular patch, update, delete. The idea here is essentially being like, yeah, this kind of request, we are just going to be proxying them through. So again, we're going to hit the version marker store. We're going to find the store where this object exists, replace the resource version that we have observed at the multi-cluster layer with the actual one in the underlying cluster, and forward the request back. And this is how, again, we are enabling like mutating request. On top of this, we are also supporting logs and exec via essentially like the same methodology. Therefore, like our user can do whatever they are used to do in an individual cluster with their pod object, just at the multi-cluster level. And I'm talking about pod. You will see this is beyond pod. This is something we can extend like to any kind of resource type that we want to abstract away from the multi-cluster layer. So into the demo. Let me just go through what I have here. So what I have here, I have two kind cluster running locally on my machine. And I am running like locally, hopefully still up, this multi-cluster API server alongside etcd and multi-queue. Now, the first thing that I want to show you is the kind of abstraction that we have at the multi-cluster layer to model like the underlying clusters and also model like this, define the object that we're going to be sending through this version marker like storage. API aggregation essentially is the API that we use to define which object we are going to be aggregating up at the multi-cluster level from the individual cluster. And API endpoints is essentially the API that we use to register with the multi-cluster layer what are the underlying cluster that we want to sync essentially like resource version into version marker at the multi-cluster layer. If we look at what this means, like how these things translate to multi-queue, what we have a controller that essentially generates for each API endpoint a multi-queue cluster configuration, which is essentially the API the multi-queue is using in order to do like register the cluster and being able like to do multi-cluster, essentially like dispatching of the workload across the clusters. Now I'm gonna show you like what the version marker are. And as you can see, version marker today is a cluster scope resource. And what we have here, we have essentially like a series of objects. And if you look at the column, they tell us essentially what is the cluster where the object exists, what is the resource version that exists at the multi-cluster layer of this object, and what is the version that exists, the resource version of this object in the individual cluster. So store RV reference like to the actual cluster where the object is present. You see here we have two kind of type of version marker. We have bookmarks, which we use in order like to keep continuously like tracking the version of the storage of the underlying cluster. So even if we don't receive any pod event, because like in my demo I've not done anything like for 30 minutes, like we still keep and being able to resume efficiently watches like when like the when there are no events or no changes for this specific store. And for the rest, we also have, like, again, a mapping for every pod object, which is essentially, like, in this case, what is configured for us to sync. So if I were to create here now a job and a deployment, what I can do get pods. And what you can see here is that I'm going to be able to see the pods. And if I do get pods minus O wide, you will see that these pods have been assigned to different cluster. You see, like, I'm using kind, so it's cluster name, node name. So you see these through the same multi-cluster API, thanks to multi-queue, essentially these objects have been like assigned to different nodes. I can watch pods again, and hopefully the job will terminate. And you will see that it's going to be, here we are, like a sequence of events that, again, like we have been able to get because the pod object terminated in the individual cluster, in this case, local A. We receive an event at the multi-cluster layer. We register this event, and then we've been able to stream it back to the client and the multi-cluster. And let me just get a thing. And if we want, I can do logs. I can get logs from my pod. I can exec into my pod, and pretty much same way that I can essentially like in a regular Kubernetes cluster. All of these interacting to the multi-cluster API. All right, so this is pretty much where we are. So we have wired this multi-cluster logic into the API server, and now we're able to abstract the placement of the object across different clusters, aggregating them at the multi-cluster level. This is not a done project. There is a lot of work in this space. A lot of work is being driven by SIG multi-cluster. A lot of work is also like things that is important for us, like as a platform to provide to our user. A lot of the things are also things that we are not working in SIG multi-cluster, and we would like to kind of start the conversation. In particular, we would like to provide like a way to share workloads across cluster. Right now, like each workload type gets dispatched on an individual cluster. If you have very large batch jobs, you might want to chunk them and kind of distribute them across underlying cluster to increase the ability to kind of fit them in the cluster. As we do this, networking and multi-cluster services will become a feature that we need to provide, and it's something that we've been looking at. We run a platform that has a mix of batch and stateful workload. One of the areas we want to work on is also like a multi-cluster attach of like volumes. And that's pretty much it. We have 3 minutes for questions. I also want to say that we are hiring, so if anyone is interested into this, like, please come to me. Perfect. Can you get to the microphone? So it's going to be recorded. Thank you.
Thanks for the great talks. In your demo, it just shows the pod resources. Does it support other custom resources as well?
Yes. So I showed it earlier. Like the key of it is essentially this API aggregation object. So you can create. I'll just show you what it is actually. The API aggregation object is essentially made this way. It's telling you what is like the kind of the object, and the scope of the object, and the cluster from which you want to kind of aggregate these resources. And this is what drives the thing. And the idea here is that the workload are defined at the multi-cluster level, so the deployment is stored in etcd at the multi-cluster level. But then the pod objects are actually like sync up, and that's essentially the idea here.
So that means that we can use the other resources.
Yeah, you can imagine like an example. If you have like service accounts, and for whatever reason you want to aggregate up service account, it's something you could do. Probably not the best one, but there are many kind of use cases for that. Imagine in your model you want to push down deployment for whatever reason, and just aggregate them up. You can kind of do it with both core types and CRD API types.
And then that aggregated data will be saved in the separate storage.
Exactly. So what you will see here, you will see in the virtual marker are prefixed by essentially API aggregation name. So you will see the virtual marker here. You can also store these, and this is one element for scalability that is important. You can store them in different etcd, pretty much as you do with events, right? Like, and we have a way to route them as well.
Thank you.
Thanks for the nice demo. Where do we have a choice to pick which cluster, what configurations it goes? How does it pick the clusters?
Yeah, so MultiQ right now is, MultiQ provide already like heuristic for doing that. Like you can, in MultiQ by default, decide that you're going to be sequentially trying in each cluster to place it. What happens is the MultiQ uses the workload. Let me just show you. So the workload as a abstraction object type as an abstraction of the specific application. And what happens is essentially that MultiQ is the multi-cluster scheduler, so it takes care of the placement. There are actually MultiQ abilities to extend this, like providing your own placement logic is something that the community is working on, like on providing the flexibility. Some use cases we have been thinking about, we would like to taint a cluster so that no new workload gets sent there, because maybe it's a cluster we want to drain or we want to do maintenance. The idea is that MultiQ has some abstraction. The community is also very eager to kind of figure out these use cases, but that's the layer where the feature gets implemented.
So how are you propagating the reconciliation at the destination cluster to the multi-cluster?
This is, again, something that MultiQ does. Like today, the way that it does it is essentially syncing, right, pushing down the spec and syncing up the status. That's the way that reconciliation works, so that you can always have, you have two copies of the object, but the spec is what you push down and the status is what you aggregate up. So your user virtually have one view of consistent view of the resources. Again, we found, because we have like some weird internal APIs that are not really respecting the idiomatic way, that we need like some custom logic. And this is something we've been talking with the community on, kind of like how to allow to extend this sync logic also for these use cases that are not like super nice, but are just API that exist and we need to be able to support.
Yeah, this is great from the command line perspective. Do we have any kind of similar functionalities where we can see the UI?
I mean, you
because
can,
the Kubernetes dashboard supports only one cluster UI.
But the idea here is that, like, again, you can deploy the Kubernetes dashboard here, and it's just going to work. Like, you can use KNS. KNS is going to be just work, because this is a Kubernetes API. From the point of view of the multi-cluster API, it's like you have one cluster. And then, again, like right now we use non-names for like providing the cluster information. You can think about like doing whatever you want, like potentially labels. We've been talking about this thing. But the real thing here, the command line is just an example of a client. kubectl doesn't know that there are many clusters here. It's just like one config. And the same way like the dashboard can work.
Thank you.
All right, awesome. Oh. Brilliant. Go for it.
Sorry, one last question.
Sure.
So do you mind explaining like where the components are running? Like in the target cluster, what part of multi-queue runs and what is the API workload or whatever you were describing before? Where is that running?
Right. So multi-queue is made by two parts. Like you have, so queue is queue manager, controller manager is the piece. And you run two copies of them. One copy, which is using a kube config pointing to the multi-cluster API server. And in each of the underlying cluster, you run also like queue, like without like multi-queue enabled. And the idea there is that queue uses this because, again, the medium that is used to to do the mission of quota, of capacity, is the workload object. So you need in the underlying cluster queue in order to understand whether the workload can be admitted, meaning that there are resources to satisfy its requirement or not. So these are like the two pieces that exist there. So we run two versions essentially of queue and just using different kube config to point them to different API servers.
OK, that makes sense. Thank you.
All right, perfect, awesome.
All right,
Thank you so much.
Next session is at 1:45.